Just a similar plot for polarization. So sorry, this is a little bit small, but this is currently the sort of best measurements we have of the cross-correlation between temperature and polarization and the E-mode polarization itself. And you can see that although WMAP's done quite a good job on very large scales in the cross-correlation, there's an awful lot of room for improvement in this figure. It's about what the temperature measurements looked like about 10 years ago. This is what we forecast for Planck. So a very nice characterization of the cross-correlation and quite a nice job on the E-mode polarization as well. The only parameter I'll highlight here that is sort of enabled by these measurements of the E-mode power spectrum is the reionization optical depth. So Planck ought to determine this to about 5% precision by using this bump, which is shown on the inset here, on very large angular scales. And I mean, if you contrast that to the WMAP measurements, Planck will be cosmic variance limited on its reionization measurement. Okay, and then for the B-mode spectrum, well, we're currently in the sort of era of upper limits. So these are all the upper limits that we currently have. And the curves here are, again, the lensing signal, and then what the upper limit from gravitational waves would be in B-mode polarization, where this upper limit is currently coming from temperature anisotrophies and other external data. So what you can see from this actually is that B-modes are currently not very constraining. They're not as constraining as the temperature anisotrophies for gravitational waves. But we're sort of at an interesting time. So last year, the BICEP data came out, which is the red points in this figure. And just from using the B-modes alone, they were able to constrain this tensor-to-scalar ratio at 95% to be less than 0.73, which isn't that far off this constraint of 0.24 that you get from using CMB and distance indicators. And over the next 3 or so years, this situation should sort of turn itself around so that the B-modes actually become more constraining. So for example, Planck might achieve about 0.05. This is just a sort of forecast for how well Planck would constrain the B-mode spectrum, and this again is for an R of 0.24. And you can see that you're getting a few sigma detection of the gravitational wave signal, but not very good constraints at all on the gravitational lensing B-modes. Okay, so just my final slide on Planck, just to give you a schedule for where things are. In October 2010, that's when the nominal mission ends, so that's the end of the first 2 surveys. And following that, in January next year, there'll be the first data release, which will be an early compact release source catalogue. So this contains basically a few hundred point sources with these sort of objects, and around 100 SZ clusters. These clusters will all be sort of independently verified, so they'll either have optical or X-ray identification already. At the same time, there'll be a large number of what we call early science papers, which will basically be dealing with properties of this compact source catalogue and also galactic science. In February the year after, so 2012, that's when the end of this 4 surveys, this extended mission occurs. And following that, at about the end of 2012, is when the first sort of cosmological data release will come out. So this will be the data, a legacy catalogue of sources, maps of the microwave background, and obviously a whole set of papers. And then the current plan is a year after that to basically do the same based on the extended mission. Okay, so let me move on now to talk about CMB lensing, particularly in the context of Planck. So what lensing does on the microwave background is it takes the sort of image which is imprinted at the time of recombination and just remaps it according to the deflection field, which is just, in the Born approximation, just the gradient of the usual gravitational potential projected along the line of sight. And because surface brightness is conserved, literally all you do is remap the temperature. So the lens temperature along some line of sight n is the unlensed temperature along the deflected line of sight, and similar things for the polarization. So the source plane here, right, is at redshift of 1090. It's the surface of decoupling. So if you compute what the deflection field looks like at that distance, it has an RMS which is about 2.4 arc minutes, and it's coherent over large scales. These are typically 100 megaparsec lenses at a redshift of about 2. So the deflection power spectrum for the micro background lensing basically looks like this, and it's basically linear with some small non-linear corrections on small scales. So what lensing does on the CMB, as I said, is to move things around. So if you just imagine making a sort of Taylor expansion in the lensing deflection, your lens CMB is the unlensed plus a product of the gradient of the unlensed temperature with the lensing deflection. And just in pictures, if you start with your, this is your lens CMB, and the difference between this and the unlensed CMB is shown here, blown up by a factor of 5. On the right-hand panel, we've got the deflection potential psi, whose gradient gives you the deflection angles, which are these little vectors. So what you can see is that the change in the temperature due to lensing is this very sort of non-Gaussian structure, as you would expect, because it's basically a product of two Gaussian fields. And if you squint at this a little bit, you'll be able to see the correlations between this field and the lensing deflections. So the main effects of lensing on the CMB are just summarised here. So you're basically looking through frosted glass when you look at the surface of glass scattering through large-scale structure. So it tends to smooth out features. So it smooths out acoustic oscillations in the power spectra. It also generates power at small angular scales, and quite importantly, it generates B-mode polarisation, even if there was no B-modes there originally. And it does this, as I'll show shortly, with an almost white noise spectrum. It also generates non-Gaussianity, as we've just seen, and the following talk from Anthony Lewis is going to talk in more detail about the bispectrum that is produced from the correlation between the integrated Sachs-Wolf effect and lensing. It also generates a 4-point function, which is rather more important. And this actually allows you to reconstruct something about the projected matter distribution by looking at the lens CMB itself. So this is something I'll return to shortly. Okay, what should we actually care about lensing? Well, there's a whole list of reasons. First of all, it has to be there, so this is an important consistency check. You have to account for it, so if you don't, at Planck sensitivities, you bias several parameters at the sort of 1 sigma level. If you're searching for gravity waves via B-modes, then it acts as an additional noise source, which corresponds to sort of having an extra 5 microkelvin noise in an arc-minute pixel on your map. Perhaps most interestingly, it provides additional information that's actually degenerate in the primary CMB anisotropies. So examples of this are constraints on light, neutrinos, and dark energy. So this is just illustrated here in the bottom, where I'm showing, if you look at this panel first, this is the fractional change in the temperature power spectrum when I change the neutrino mass by 0.1 eV, so that's the black curve, and the equation of state of dark energy by 0.2. And I've done this keeping the angular diameter distance to last scattering fixed. And because of this geometric degeneracy in the microwave background, the only effect on the temperature power spectrum is really coming from the late time integrated Sachs-Wolf effect on large scales. The error boxes here are cosmic variance errors. So what you can see, disentangling these two would be very, very difficult, basically impossible because of cosmic variance. However, if you look at the same fractional effects in the lensing potential power spectrum, then you can see that you can clearly disentangle these two effects due to their different scale dependence. So in principle, by mapping out the lens CMB, you can use this non-Gaussian property to reconstruct the mass distribution projected all the way back to recombination, which I'll come back to later. And something I won't have time to say, which is potentially very interesting though, is you could learn something about the masses of very high redshift clusters by using the CMB as a very high redshift source plane. Okay, since this is a conference mainly focused on cosmic shear galaxy lensing, let me just draw some comparisons between CMB lensing and galaxy lensing. So we have a single source plane, like a sort of fixed redshift determined by the decoupling epoch at recombination. And one very important thing is that we understand very well the statistics of the field that is being lensed. So we know typically what size the blobs in the microwave background are, we know what their characteristic scale, shapes are, and it's all predicted by linear theory. And in particular, since we know the scale of objects that are being lensed, magnification information is just as important as shear. So actually, I won't say much about magnification or shear separately at all and just work directly with deflection angles.